In this lecture, we talk about double linked lists. In the previous lecture, we talked about single linked lists and applications of single linked lists. When it comes to the disadvantages of single linked lists, it can be observed that once we start at the beginning, we can continue to trace along the nodes of the single linked list and we can reach the end. But at any stage, we cannot come back to any of the previous nodes. To avoid that, we come across the circular linked list. There again, if we want to go back, we have to go around the entire single linked list until we reach the required node. To alleviate this problem, we can have a different kind of linked list where we'll store two memory addresses instead of one memory address which is pointing to the next node. If we can store two memory addresses, one is pointing to the next node and the other one pointing to the previous node. So in this case, we call them as double linked lists. So at every node, we'll have the data and two addresses which is pointing to the right node and one is pointing to the previous node. So next node or previous node. Here we have an example here. We have a head node is there 2040 and null is there in the previous address node here. So it being the starting node, there is no previous node for this. Null is placed at that location and then 2030 is pointing to the next node. When it comes to the node B, 2040 is pointing to the previous node now. 2040 is the previous node, 2034 is the next node. Like this, we can have a number of double linked list nodes, and the last node of the double linked list again shall consist of null in the next node, whereas in the previous link we'll have the previous node 2036. So like this we can create double linked list. When it comes to the operations on the double linked list, again we can traverse through the double linked list. We can insert before the current head of the double linked list. We can have insertion at the end of the double linked list, and insertion at a location can also be done. Okay, given a double linked list, how do we insert at the head location? Is we need to create a new node with two links. One is pointing to the current head because we need to add this node at the beginning. One is pointing to the current head, and the previous node link of the node is empty because it being the new head. Okay, when it comes to the logical part, we create a new node as a create node, and then next of new node shall be head because the current head will be added to that, so that this becomes the head and a continuation is maintained. And previous link of the new node shall be made as null, and previous link of head, the already existing head whatever is there, that should become the second node actually. So in the previous link of head, this new node has to be pointed. So previous link of head shall be new node, and the new head should become the new node. This is how we'll create a insertion at the beginning. Now when it comes to the insertion at the end, again given the linked list, the head is given as an input. We need to traverse through the linked list, double linked list, until I reach the last node. So the traversal is done, temp is taken as head, and while temp not equal to null, keep on tracing, maintain previous is equal to temp and temp is equal to next link of temp, so that this will enable us to pass through all the nodes until we reach the last node. Now once we reach the last node, we need to create a new node here. So new node is equal to create node, and once new node is created, that should be appended to the as the last node. So for that, next link of previous node, whatever the last node is there, that is stored in the previous node. So next link of previous shall be this new node, and previous link of new node shall be previous, and next link of new node shall be null. That is insertion at the end. Now when it comes to the insertion at a location, if you find a data B, then insert the node after the node. So if that is the case, the same process will be done. Instead of tracing to the last node, we'll trace with respect to the data until we reach data equal to B. So input is taken as head and temp is equal to taken as head, and while data of temp not equal to B, we keep on tracing through the double linked list. Once we reach there, we create a new node is equal to create node, and then here this node has to be in between the existing nodes. So for that, next link of temp is taken as new node, and previous link of new node is taken as temp, and next link of new node is taken as next link of temp, so that this will be added in between the existing nodes after B. Two more operations are deletion can be done again. Deletion at the beginning of the double linked list. Deletion can be at the end of the linked list. Similarly, deletion can also be done at any middle location. When it comes to the deletion, whatever be the current head, that should be deleted, and the next node that is to the right of head shall become the new head. So input is head now, temp is taken as head, and the head is taken as next link of temp. Whatever next link is there in the head, that should become the new head, and previous link of head shall be made as null, and we need to delete the temp. Similarly, when it comes to the deletion of the last node, start at the head node, keep on tracing until you reach the last node. So temp is equal to head, while next link of temp not equal to null, keep on moving. Temp is equal to next link of temp, temp1 is equal to previous link of temp, that is also maintained to identify the last node. Once that is done, once we reach the last node, the previous node to the last node shall be made as the last node. For that, next link of temp1 shall be made null, and that breaks the link between the two, and the last node, whatever is there in the temp, that has to be deleted. This is how we delete the last node. Similarly, if you want to delete the middle, similar process can be done just by removing and trace the linked list until you reach a location, and then alter the links and remove it, delete the. Just like in the case of single linked lists, we can also make the double linked list circular by placing the head pointer value in the last node as next link. So once we reach the last node in the next link, if we place the head value, it points to the starting node again, so that it makes circular. So whatever operations that we can perform on the circular linked list can also be done in the circular double linked lists. So this adds more power of tracing and reaching the nodes in case of double linked lists. When it comes to the applications of double linked lists, sparse matrix representation is one of the best applications of double linked lists. A sparse matrix is a matrix in which the number of non-zero elements are very minimal when compared with the total number of elements available. Here is an example. We have 5 rows and 4 columns, and of which only 5 values are having non-zero values, and all the remaining values are 0. So when compared to the total values available, only 5 values are non-zero. This can be treated as a sparse matrix. The disadvantage of sparse matrices is that if you want to perform operations of addition or multiplication or any other operation, the number of non-zero values are very minimal, and it is computationally heavy when compared to the available values. So if we have a better representation, then so that we can save time, time complexity of the operations will be better. To store this information, we can use double linked lists. The head node can be represented consisting of information about the matrix, like number of rows, number of columns, and the number of non-zero values. So 5 rows are there, 4 columns are there, and 5 non-zero values are there. 4, 5, 5 is the information that is stored in the head node. From this head node, we can have column links and row links. If you observe the matrix here, the first column, second column have non-zero values, whereas the third column do not have any non-zero value, whereas fourth column is having one. Now it is enough if we represent first, second, and fourth columns to have the information. Similarly, when it comes to the rows, first row is having non-zero value, second row is a 0 row, third, fourth, and fifth are non-zero rows. So we can avoid second row. To indicate this, we have 0, 1. We have link, next node link to 0, 1, the second node, which indicates first column. 0, 2, second column. 0, 3 is missing, so it's a 0 column. 0, 4 is a fourth column. So this 0, 1, 0, 2, 0, 4 indicates non-zero column information. Similarly, when it comes to the rows, 0, 1, 0, 3, 0, 4, 0 and 5, 0 are the non-zero rows. So these nodes will indicate row information, and above 3 indicates non-zero column information. Now, when it comes to the location of the elements, 1 is present in first row, second column. So we can have links from first row node and second column node to this node having data value 1. That is represented in the diagram here. 1 is the data value which is having links to the first row and second column. Similarly, third row, second column is there. Third row, from third row and second column, we have links to the node third row, second column. In the same row, we have one more value is there in the fourth column. So third row, fourth column element again having 2 value. So there is a link to 5, the data value 5. Similarly, 9 and 6 are represented, and 7 is represented in the fifth row, first column. So like this, whenever data is present, they can be represented there at the corresponding nodes with the corresponding nodes, and all the 0 information can be deleted. So that whenever we want to perform operations, now we know the information about the matrix, and we know the locations of the non-zero elements, and the data that is present at the non-zero locations also.